In this lesson, we're going to talk about linear quadratic systems. So I'm just going to outline the three ways that we can find where a line crosses a parabola. So the first way is algebraically, which is the most accurate. Graphically, we're going to do this below, we're going to do graphically, and then substitution is when you're just doing guess and check. So let me show you what I mean here. Draw a diagram to show a line and a parabola intersecting twice. So let me draw a parabola like that and then a line like this. This is kind of the most common scenario where we have them intersecting twice. Now we can actually see these intersecting twice, but what if I had a line that I couldn't physically see it intersecting twice? Let me just get rid of this line here and put another one up. What about this line? Would that intersect twice? It would. It would intersect twice up here somewhere. So even though you might only see one point of intersection, there is often two. Now how about a line and a parabola intersecting once? Okay, let's do a different quadratic here. Let's do a wider one. There's a quadratic. Now a line intersecting once. So the easy, an easy one to do here is kind of maybe coming down like this. That's only going to intersect once, and even if we imagine the parabola growing to infinity in both directions and this line going down, the parabola is going to continue to get wider, so this line's never going to cross it again. There's also another scenario that we call a tangent. So if I put a point right here, now I want a line to just cross at that dot. So if I'm going to draw a straight line that kind of skips off of that line there but doesn't actually cut through, that line is called a tangent line. And it also only has one point of intersection with the quadratic. Now the last option is a line and a parabola not intersecting at all. So let's do parabola like this, and then I'm just going to put a line below it like that. They're never going to cross. Even as both of them continue on to infinity in both directions, they will never intersect. So these are your three possibilities, the three ways. Sorry, those aren't the three ways. These are three ways to find out graphically, but we haven't talked about algebraically or substitution yet. Our next example we're going to do is algebraically. I'm going to go over how we can algebraically see how a line and a quadratic intersect. Example 1. Determine the point or points of intersection, if any, for this pair of functions. So we can use decimals here. We've got f at x and we've got n at x. One is a quadratic, you can see that by the power of 2, and this one is linear. So do they cross? How many times? So algebraically is how we're going to solve this one, not graphically. The first thing I do is I make the two equations to equal each other. So I'm going to write f at x. I want to know where it's equal to n at x, and that will be a point of intersection. Where the two functions equal each other, they have, for example, in the graph above, these would have the exact same coordinate here. Let's say the coordinate there is 3, 4. So both the parabola and the line have that exact coordinate. So that's why we're setting them equal to each other. So that's negative 2x squared plus 3x minus 1 equals 6.5x minus 3. So we're going to bring everything over to one side and set it equal to 0. Which side do we bring everything over to? Does it matter? It doesn't matter, but one way is easier than the other. It's usually standard to want to have whatever your highest power is, this one here, your x squared, you want the number in front of it to be a positive. That usually makes things easier. So that means I'm going to bring everything over to the right side. That way I'll have a positive, it's called a leading coefficient. I'm going to have this 2 being a positive rather than a negative, but it doesn't matter which way you do it. So I'll have a 0 on this side, and when everything comes over, I'm left with a positive 2x squared and plus 3.5x and then minus 2. So now we have a new quadratic, and I want to find out where this is equal to 0. That will tell me where these two original pieces were equal to each other with my new function here. I'm not even going to try to factor that. I'm going to use the quadratic formula. x is equal to, and everyone has it memorized, so I'll just sub in negative 3.5, negative b, plus or minus the square root of b squared minus 4 times the a value times the c value, all over 2a. So right now I want you to get out your calculators and work this all out, and I will show you the answers that we get. So we get x is equal to approximately, I'm going to put a dot up top of the equal sign for approximately equal to. We get two answers, take 4 decimal places for now, 4,538. Well, it says rounded to the nearest thousandth actually, so I can round that. Let me just change that. Make that a 4. And my other answer is negative 2.204. But we're not quite done because the question said determine the points of intersection. All I found is the x value. So if I were graphing this, all I would have so far is, do a little sketch here. If I were graphing this, I would have an x value of, let's see, that's negative 1, negative 2, 1. So I've got an x value of 0.4, so somewhere here, I don't know the y value, it's going to intersect somewhere there, and when x is negative 2.2, so somewhere here. Those lines are supposed to be straight. So I don't know where. Is a point of intersection here and here. I need the y value. I only have the x value, so I could have say my parabola is going like, going like that, and my line was going like that. If they were straight, I need to know those 2 points of intersection. Let me erase that. All right, so I've got the x value. How do I find the y value? You did lots of this in grade 10. You sub it back in. So I can sub my first answer into f or into n. So I can find f at 0.454, or I could sub it into n, 0.454. So I could sub it into either one of those. I should get the same answer because it doesn't matter if I sub it into the quadratic or into the linear equation. It's a point of intersection, so we're going to get the same answer no matter what. So when you do that, well, why don't you go ahead and do that, and I will tell you what you should get. So we should get the coordinate 0.454, comma, and then the y value is negative about, now we do some rounding here, negative 0.050, I think. So that's 1 point of intersection, but there are 2. We have found that there are 2. So we've got this situation here. We have to find the other point of intersection. So we're going to take our other answer and sub it into either one. So you're probably going to want to sub it into the linear one. That's a little easier to sub into. So we sub it in, 6.5 times negative 2.204 minus 3. And we get our second POI, therefore negative 2.204 and negative 17.32 is the second point of intersection, POI. So that's how we algebraically determine where the points of intersection are. All right, we only have one more example here. Example 2, determine the values of k such that the linear function g at x does not intersect the quadratic function f at x. Step 1 is we're going to set f at x equals g at x and put all terms on one side. So whenever you're looking for a point of intersection, it means you're looking for where two functions are equal to each other. When they intersect, they have the same coordinate. So we start with that. F at x is negative 3x squared minus x plus 4, and g at x is 4x plus k. I want to bring everything over to one side, and it doesn't matter, but I'm going to bring it all over to the left side so that that 3 that's in front of the x squared becomes a positive. 3x squared comes over, plus 5x, and then I have this other weird stuff. I have that plus k, and then I subtracted a 4. This k is, let me circle it here, this k right here is a constant. I know that it's a constant term, like the minus 4, because there's no x with it. If there were an x with it, then I would have to group it, then it would be grouped together. I would have something like, right here, I might have 5x plus kx or something, right? But there's no x on it, so I know that it's a constant, so it's going to go with that value there. Okay, so I've got everything over on one side. Now, look at step 2. Set the value of the discriminant is less than 0 and solve for k. Why? Why are we doing that? Well, the clue in the question that we're using here is, it says they do not intersect each other. So if they do not intersect, that means, well, let's look back up here for a second. These ones intersected, and when we solved here, we had this plus or minus. We got 2 answers because the discriminant was positive. So that when the discriminant is positive, you're going to get 2 solutions. When the discriminant is negative, we're going to get no solutions. That's why we want our discriminant to be less than 0. So I would need my discriminant to be less than 0 because that means no points of intersection. No points of, short for intersection is this xion. So no points of intersection. Okay, so now what's the discriminant? Discriminant is b squared minus 4ac. That's got to be less than 0. What's b? Okay, I'm going to label these up here. The 3 is my a, the 5 is my b, and these two together are my c value because they're both constants, remember? So in for b, I don't need brackets because b is already positive, so 5 squared minus 4, now I am going to use brackets, times 3, and my c is k minus 4. And that's got to be less than 0. So we get 25 minus, this is going to give me a 12, times k minus 4 is less than 0. And I can distribute that 12 in, but I cannot do 25 minus 12, right? Order of operations. So let's distribute the 12 in. Minus 12k plus 48 is less than 0. Now we can go back up to the step 2 here. We're going to solve for k. So I'm going to bring the 12k over because remember that negative thing we talked about before in section 3.6? I don't want this, because I'm dealing with an inequality, I don't want a negative with my k values. So I'm going to take the 25 and the 48 together. That's 73 less than 12k. So I added 12k to both sides so that I could have a positive here. If I didn't do that, this step I'm going to do now, which is divide by 12, if that was a negative 12, I'd have to flip my inequality sign around. So I get, these cancel out, I'm going to rearrange it so that the k is at the front. I get k is, now I've got to get my sign right. My answer is 73 over 12, or we can put 6.1 here instead of 73 over 12. I've got to make sure that the small part of my inequality, the pointed part, is pointing to the number, right? So the pointy part here is pointing to the number, so here it has to be pointing to the number. So k is greater than 6.1. So if I have any value of k that is greater than 6.1, like 6.2, then that quadratic and line up here at the beginning, they are not going to intersect as long as I have a k value greater than 6.1. And I'm going to show you this on Desmos. Here, if I can fit this in. A little bigger. Sorry, this is example 1, not example 2. So look back at your example 1. This was the original question here. We had negative 2x squared plus 3x minus 1. That was our original quadratic. That's in red here. That's the red one. That's the parabola. And then the line we had was 6.5x minus 3. So if you were graphing these by hand, you would graph these two pictures here. And then their point of intersections, well, Desmos gives me kind of a gray dot to show me the points of intersection. And look at those numbers there. They're pretty close to the numbers that we got. We did some rounding. So those are the points of intersection. So we didn't actually do two separate equations and work with them separately. We brought everything over to one side, remember? So when we did that, we had this equation here that you're seeing now in green. This equation. So when we put our quadratic and our linear together, we got a new corresponding equation. And this one here is completely different. It looks like this. But this allowed me to look for zeros instead of looking for points of intersection. And the zeros are the same as if I had kept them separately and graphed them separately. So graphically, you could graph them both separately, as we originally did here. Graph them both separately, look for their points of intersection. Or you could graph it, put the equations together and graph it as one. But you're going to look for the zeros in that case. If you need some review on this, I would go back to 3.6 where we talked about discriminant questions, and you can always review your solving equations or your quadratic formula, which was also in this unit as well.